Hey guys, how's it going? In this video, I'm going to be going over multiple linear regression from scratch. I'll be going over the math, intuition, and then implementation in Python. To do this, I'll start with just linear regression, and I'll start with like some example data and how making predictions works with linear regression. And then I'll go into the cost function and gradient descent, and then from there, I'll expand it out into multiple linear regression, which has multiple X features, and that'll have an updated cost function and gradient descent as well. So let's get started with just normal linear regression. Alright, so let's start off linear regression by just coming up with some example data. I'm going to use house data, specifically the size of a house and the price of it, and I'm going to use some very small numbers just to keep calculations in the future simple. So we're going to do the size of a house and the price of a house. Some sizes are 1, 3, and 4, and the prices of these houses might be 2, 4, and 8. And notice how each house and its price is in a row by itself, so we'll label these with I, starting at 1, going down 2 and 3, and if we had a bunch of houses, the length of them would be of size m. And we have x as our size or our feature, and then our price or label would be y. And just for extra notation, if we were looking at the size of the ith house, we might say x at I. So if we said x at 1, that would give us a size 1. If we said x at I2, that would give us size 3. And the same thing could be said for y, or the price. So y at I is the ith house price, where I at 1 is equal to 2, and y at 2 is equal to 4. Now I'm going to go ahead and graph these points so we can visualize them. So we have a point at 1, 2, a point at 3, 4, and a point at 4, 8. And notice that the x-axis is size, and the y-axis is price. Alright, now that our graph is set up, let's say we're given a new house of, say, size 2, so a size right here, and we want to predict the price of that house. Well, one thing that you could do is create a line of best fit given all the existing data, so that might look like a line like this. And once this line is plotted, we could say that a size of 2 might correspond with a price of 4. And then we can also go ahead and write the equation for this line, which in linear regression, this best fit line would be represented by y hat equals wx plus b, where w is considered the slope and b is considered the y-intercept, but in our case, w would be called weight and b would be called bias. And then also notice the y hat has a hat on it because this is a prediction line and not the true value of y. The true value would be present in this price column right here. But now that we have this example data and this line plotted, let's go ahead and code that up in Python. Alright, so I just opened up a blank Jupyter notebook, and if you're unfamiliar with how to set one of these up, I would recommend finding some tutorial online. There's a ton of tutorials out there, and once you do, I have a few packages installed. I'm going to be using NumPy, scikit-learn, and matplotlib, so I'm actually going to go ahead and import those right now. And notice I'm going to be using the low diabetes dataset from scikit-learn, and we'll be touching on that a little bit later once multiple linear regression's all set up and we're ready to scale out. So I'll import those, and we will start with just basic linear regression. And now we can initialize our X features and Y labels, and then a weight and bias. And I'll go ahead and use these same values that we have here. So 1, 3, 4. And 2, 4, 8. Alright, and now to initialize a weight and bias. So if we come back to this graph right here, we'll notice that W is the slope and B is the y-intercept. And from this graph, it looks like the W might be something like a rise of 3, a run of 2, which that would give us W equals 1.5, and B, it looks like lands around 1. So let's go ahead and initialize W and B. Alright, now that we have those variables set up, we can go ahead and make some predictions. Alright, now let's write a function that predicts y hat given x, w, and b. And we are going to be iterating through all m rows in x. And we're going to be outputting m y predictions. So initialize an array of that size. And then we're going to iterate over the size of each house and then predict a price for each of those sizes. And once we've made all those predictions, we can go ahead and return y hat. So let's go ahead and try to make some predictions now. Alright, so when we feed in x, w, and b to our predict y function, we get these three values. And let's actually compare those to our true y values. Alright, so we've predicted 2.5 when y was actually 2. We predicted 5.5 when y was actually 4. And 7 when y was actually 8. And now let's plot this just so we can see how our predictions compare to the actual values. And as you can see, there's an error between y hat and y true for each of these points. So next, let's calculate how bad this error actually is back in our whiteboard. So as we saw a second ago, these true points that are scattered have some error between them and the predicted point. And if we wanted an equation that could tell us how bad the error is, then we would use the mean squared error equation. And while this is the mean squared error equation, it's common to put a 2 down here, just a constant, and this will clean up some derivations later on when we get into the calculus portion of this. But for now, let's try to dissect what's happening. So we have y hat at I, which might represent a point on our predicted line, and then y at I, which would correspond to the actual true value at the ith index. And what we're doing is we're seeing how far apart this predicted value is from the true value, and then squaring it, which will make the error positive and of higher magnitude when the error is larger. And notice that this is the mean squared error, so we're going to then divide each of these summed parts by the number of parts, and that'll give us the mean squared error. So let's actually try to calculate what our mean squared error is for our scenario here. All right, and if we have mean squared error is equal to 1 over 2 times m, which is 3 for our case, times the sum of the predicted values minus the true values squared. So 2.5, the true value was 2 squared, and then we want to add the next one, 5.54, and then finally the predicted value is 7 when the true value was 8. Okay, now we can clean this up a little bit. And if you continue to work this out, you'll end up getting 0.583 repeating. And that is our mean squared error when we have a weight of 1.5 and a bias of 1. So let's go ahead and code this out in the notebook and see if we can replicate these results. All right, this section will be the mean squared error cost function. And we'll write a function for this. So the first thing we want to do is calculate y hat, and then sum the squared errors, and finally divide them by 2m. And we can go ahead and return MSE. Now if we plug in our values to calc MSE, then we should end up getting 0.583 repeating like we did earlier. Oop, I just forgot to include m. There we go, and we got 0.583 like expected. And going back to the whiteboard, just one more addition to make. Typically in linear regression and in machine learning, the cost function is denoted as j, and we have w and b as the inputs. And this is our cost function. And at this point, we can actually move into gradient descent. And so to start that off, I'm going to come back up to our graph up here. And recall that each of these y trues had some error to the y hats. But let's say we had a w value of something much less, like w is equal to 0. Then notice how the error between each of these points is much larger. And so the mean squared error as a result would become much larger. Similarly, if we had a w that was way too steep, then the error here would also be very large. And maybe this line has w equal to 5. Then at this point we can actually create a new graph. And in this graph we will have, let's just put w on the x-axis and then j of wb on the y-axis. And actually, for the sake of this graph, let's ignore b and just look at w, just to fully understand how the cost function might be working with different values of w. So as we saw previously, when w was 1.5, so let's say this is 1.5, then j of w was relatively small. It was only about 0.5 or 0.6. On the other hand, when w is equal to 0, our errors were much larger, and so was our mean squared error. So that might give us a very high j value. And similarly, when w was equal to 5, we also had a really large error and large mean squared error. And if you kept plotting points in between this is w equals 0 and w equals 5. Let's say you had a slope of maybe 1. Then the error between the y hat and the y true is not huge, but it's not as good as 1.5. So maybe we would have a mean squared error somewhere around here. And it turns out if you kept plotting a bunch of different points for different w's and then its corresponding cost, you'd get a graph that looks something like this, which also resembles a parabola. And you'll notice when w is very high or very small, we'll have a very high cost. But when w is just right and just in between these points the best it can be, that's when we have the lowest cost. So if we have a point, say, at this w equals 5, then we would want our w value to decrease so that our cost was also lower. So instead of 5, let's shift it to the left, maybe to 4. And in doing this, our cost function yields a lower value, which is what we want. Similarly, if we're looking at a w of 0, then that'll also give us a very high cost. But if we want to move it to the right a little bit, maybe by 1, that'll yield a much lower cost, and that's what we want. The second important thing to notice with this graph is if you look at this point to the right, you'll notice that it has a very large slope, a large positive slope. If you look at this point just to the left of it, you'll notice it has a large positive slope, but not quite as large as the one to the right of it. And then these points to the left, this one might have a medium negative slope, and this one up at the top has a very negative slope. So if we just make this observation that a positive slope results in us wanting to decrease w, and a negative slope results in us wanting to increase w, then we can see that if we have some w, say w at 0, and it gives us a high cost with a decreasing slope, then we want to increase w. So that would move w up a little bit, and that would reduce the cost, and thus making this line closer to the best fit line that it can have. And the same would be true if w was too high, like this line right here. We would want to decrease w to get it closer to a best fit line. And calculus will tell us that to find the slope, we need to take the derivative, or in this case partial derivative, because we have two input variables. We need to take the partial derivative of j with respect to w and j with respect to b, get the slope from those partial derivatives, and then if it's an increasing slope, nudge it to the left. If it's a decreasing slope, nudge it to the right, and then hopefully converge at a global minimum. So let's go ahead and figure out how to get the partial derivative of j with respect to w and partial derivative of j with respect to b. Starting with the partial derivative of j with respect to w, we would have something like this, and applying the partial derivative to the actual cost function, now we just need to actually take the partial derivative, and that will result in the following. And now I'm just going to expand this term out so we can see fully what it is. And there we have the partial derivative of j with respect to w, and the partial derivative of j with respect to b is very similar, so I'll write that out next. So the only difference between these two is that the partial derivative with respect to w had an x attached to it, so this x got pulled out during our derivation, whereas b has no coefficient attached to it, so it would only have a 1 pulled out during derivation, or nothing in this case. So that is what we get when we pull the derivatives of j with respect to w and j with respect to b, and this would be considered our gradient. And now that we have these two equations, we can apply them in the gradient descent algorithm. So this is going to be what the algorithm actually looks like right here. And this is going to take on some form of a loop, and in each iteration we're going to take the existing w and subtract it by alpha times this partial derivative, and do the same thing for b. We're going to set it to b minus alpha times the partial derivative of j with respect to b. And alpha in this case is going to be the learning rate, which is just a very small number that will ensure that making a step in any direction is not going to be too much of a step. So if we have an increasing slope and we want to decrease w, we don't want to decrease it so much that our cost gets actually higher. We want to just nudge it a little bit to the right so that our cost decreases, and then at that point it'll get nudged a little bit more and a little bit more until we reach a global minimum. Alright, so let's go ahead and implement all of this into Python now. First we're going to calculate the gradient, and then we're going to apply the gradient descent algorithm. And I'm going to start off by writing the gradient calculation. And for this step we're going to be iterating over all m rows. And we're going to calculate a variable for djdw and djdb. These are both initialized at 0, and then we're going to go into this sum and add some values to djdw, and then finally divide both of them by m. So let's go through the sum first. And the first step we're going to do is calculate the error between the predicted value and the true value. Then for djdw, we're going to multiply an xi, and then djdb is just going to take that error. And then finally, we're going to divide both of these terms by m and return it. So we calculated our mean squared error earlier, given x, y, w, and b, and it gave us 0.583 repeating. Let's see if a single step of gradient descent will lower that mean squared error. So we're going to first initialize an alpha, which again, that's our learning rate. And now we'll make a single step to w and b. And this part of the algorithm corresponds to this inside of the repeat function that we wrote earlier. So let's go ahead and see if our cost function is any lower. And it turns out that our cost actually is just a little bit better than it was before. So that means the calculate gradient function did work, and applying it in this way did improve our cost. And at this point we can go ahead and just write the gradient descent algorithm since we know it's working. And in this function signature, I just initialize the number of iterations to 1,000, so we're going to apply 1,000 gradient steps. The learning rate, or alpha, is 0.01, just like we had up here, and history intervals is going to record the mean squared error every 100 iterations. So first of all, we're going to need to know how many rows of data there are. We'll want a dictionary for the history. And then we can start iterating over those number of iterations, which I'm actually going to add an S there. And at this point, we have applied the gradient descent steps. So let's just store the mean squared error every 100 iterations to history. And again, I'm actually going to remove this S here. Then we'll calculate the cost. Then store it into history. And then I'll go ahead and print it out as well. Okay, at this point we can go ahead and just return the history, weight, and bias. And then perform gradient descent. And it looks like our cost function went down over each iteration. So now let's plot the history using matplotlib. And from this graph, it looks like our cost significantly went down over time. And now we can compare what our new line of best fit looks like compared to the one we started with. So let's do that. And so looking at this graph, we can see the old prediction line and the new prediction line. And it might be a little hard to tell, but this new prediction line is better than the old one. All right, and at this point, we've actually finished linear regression. And what I'm going to do next is create another data set with a bunch more points so that we can see how a line fits that data. So I'm going to go ahead and do that now. And this is going to have a target weight and a target bias. Which I'll initialize those to some random values. And we want to initialize the number of training examples, so we can do that up here. We'll start with, say, 20 examples. And this random noise is going to be applied to y so that we don't have scattered points all on the same line. Okay, so that's our data set. Let's visualize that. Alright, so here we have our example data set, and let's go ahead and fit another line to this using our linear regression algorithm. Alright, now that we've fitted a weight and bias to this model, let's go ahead and visualize what that looks like on a graph. Alright, so as you can see, the model fit the data almost exactly how we wanted it. Let's go ahead and see what our weight and bias values are that we got out of the model. So we have 3.3 about and negative 1.3 about, and our target weight and bias was almost exactly that. We had 3.3 and negative 1.2, so the target bias was just a little bit off, but looks like it did pretty well. Maybe it was the noise aspect that we came up with up here, and maybe just not enough data, but overall the model performed fairly well. So I think we're ready to move on to multiple linear regression. Alright, back to the whiteboard. Let's look at multiple linear regression now. And just like we did in normal linear regression, let's start off with some example data. So let's say we're looking at house prices again, and this time we have size and age, and we are still predicting the price. And maybe the sizes are 1, 2, 3, 1, and the ages are 2, 1, 1, 3, and then the prices are 3, 6, 8, 7. Alright, now looking at this data, as you can see, we have two feature inputs, size and age, and we're trying to predict that single price output still. So before we had a single X input, say size, and that took on a single X value at each training example, but now we have two X values at each training example that we need to input into our model. And so now we want to label them separately, where size would be x1 and age would be x2. And with this new subscript right here at x1 and x2, we want to define that subscript as j. So if you have x at j, that's equal to the jth feature. And that just means at x1, you have size, and at x2 you have age. And then if you wanted to combine that with the notation we looked at earlier, then xi of j would be looking at the jth feature of the ith training example. So for example, x at 2, 1 would be looking at the second row and the first feature. Alright, and moving on. Previously, we had something like y hat at I is equal to w xi plus b. But now we have multiple features for x. Right now we have size and age, so we can't input a single value into this x of I. We're going to need to input multiple values, so something like y hat of I is equal to x1 of I and x2 of I, and then our bias remains. But now, since we have two completely different unique x features, we're going to want two unique weight values to complement each of those features. So we'll have something like weight 1 times x1 at I plus weight 2 at x2 at I plus b. And by doing this, if we have the right value for weight 1 and weight 2, then we'll accurately predict the y value. And a cleaner way of writing this would be the vectorized form, so I'm going to go ahead and write that down. And what this is saying is we want to get the predicted value at y of I which is equal to the weight vector dot the x vector at I plus b. And weight vector dot x vector at I is the same thing as saying this up here. But now that we have this equation right here, let's go ahead and implement it in Python. All right, I'm going to start a new section for multiple linear regression now. And first we want to initialize some values for x, y, w, and b. And let's just use these values that we created earlier. Okay, and notice how the X array has a shape of 4 by 2. So we have 4 training examples and 2 features, and then Y again only looks at the 4 training examples. So let's go ahead and create a weight and bias, and again our weight needs to have the same number of features as our X input. And our bias again is just going to be a scalar value. Alright, so with multiple features, it becomes a little more difficult to visualize what's happening on our Y prediction graph. And that would especially be true if we had, say, like 10 features, because that would become like a 10-dimensional plot. So what I'm going to do instead is create a plot that shows us how accurate our Y values are. But first we need a function that actually predicts the Y values, so I'm going to write that now. And as we saw in the notation earlier, we're actually doing a dot product between the weight and the x. So to do that, in NumPy, we want to say np.dot w and then x at that row. And then we can go ahead and add the bias. And then we can finally return y hat. So let's go ahead and make some y hat predictions now. Okay, so here are our values that we predicted, and let's actually compare those to the true y values. We predicted 5 when it was actually 3, 6 when it was actually 6, 9 was actually 8, and 7 when it was actually 7. So we actually got a couple of these right with just a random weight and bias, but we still have some error, especially the 5 with the 3 and the 9 with the 8. So let's first build a plot that compares our y hat to our y, and then once we see that visualization, we can move on to the cost function and gradient descent. So I'm going to go ahead and write the code out and then explain it afterward. Alright, so this function takes in x, y, the weight, and the bias. It predicts y hat, and then it creates x ticks for each training example. And then it compares the true y value against the predicted y value at each of those training examples, and then plots them on this graph down here. Whereas you can see the true y value of index 0 was 3, while the predicted y value was 5. And then at index 1, the true and the predicted value was both 6. So that's just a visual representation of what we saw right here. Alright, now that we have this comparison plot, let's move into the cost function. And to get into the cost function for multiple linear regression, I'm just going to start with the cost function we had for basic linear regression and then move on from there. Alright, so this was our original cost function, and I'm actually going to expand out this y hat term. So here we have the cost function we used for basic linear regression, and let's see what we need to change now to make it fit for multiple linear regression. So above we saw that our new function to predict y hat was equal to w vector dot x vector at I plus b. And in our current cost function, we're still looking at single values for w and x. So the only thing we really need to change is adding vectors to w and x and then taking the dot product. And then this is still going to yield that y hat of I value. So this should be sufficient to calculate the cost for multiple linear regression. So let's go ahead and implement that in Python. And again, I'm going to write a function to calculate the cost. Alright, so this is just the calculate mean squared error function rewritten using this new predict y function that we created right up here. And it should be following that same format of summing all of the errors and squaring them and then dividing them by 2m. So let's run that. And it appears our mean squared error with our given weight and bias gives us 0.625. And now that we have the cost function, we can move on to gradient descent. Now, just like we did for the y hat function and the cost function, I'm going to write down the partial derivatives for w and b given just basic linear regression. Alright, so these are the two equations that we looked at earlier for basic linear regression, but in multiple linear regression there's some small changes that need to be made, so let's take a look at those. In the top equation, we can't simply look at the partial derivative of w because now we have a vector of w's, and that vector might look something like this, where we have w1, w2, and that goes all the way up to wn. And under this notation we could say w at j is equal to the jth weight. So applying this notation to the partial derivatives, we can only be taking a partial derivative of a single weight value. So let's mark this at partial derivative with respect to wj. And then inside of the equation, there's some other changes that need to be made, so I'll add those. Now notice that in this sum part, we're now looking at the dot product of the vectors, and then the only x value that's getting pulled out is the x at index I considering element j. And the reason we're only pulling out element j is because if you expanded this dot product right here, you would have something like w1 x1 at I, w2 x2 at I. And if you wanted to get the jth partial derivative, let's say j was equal to 2, then you would only want to pull out this x at I element 2 during that chain rule. And now if we write this out as an algorithm, this will be very similar to what we had before. We'll say repeat w at j needs to be equal to w at j minus alpha times the partial derivative of j with respect to w at j. And this will occur for each element in the w vector. So for j equal to 1 all the way up to n, which n is the number of features. And then of course we want to update the bias as well. And this is the algorithm we'll be using for gradient descent with multiple linear regression. So let's code that up in Python. Okay, so first I'm going to write out the gradient descent step, and then I'll get into gradient descent. So this is going to be the function for the single step. And here m is the number of training examples and n is the number of features that we're looking at. So same thing as what we had up here. We have 4 training examples and 2 features. And at this step, we want a partial derivative of j with respect to w for each element in the w vector. So then we can apply each of those partial derivatives to our w vector, and then dj db only has one element to apply to that single element bias. And now let's iterate over each training example like we did in the previous gradient descent step, and calculate the error. Now notice that this is just calculating that y hat and then subtracting y from it, like up here where we have the y hat calculated and then subtracting the y. Now at this step we want to find the partial derivative of j with respect to w, but we want to do this for every element in our w vector. So this is going to require a for loop. And it's going to use j as the index going over n, which n again is the number of features. And at that jth index of dj dw, we want to add the error times x at ij, similar to how at dj dw at j, we want to add the error times x at I of j. And then we want to add to dj db just like before, using the error. Next, we just want to divide both of those sums by m. And we can go ahead and return those. And one last change I'm going to make is comment this out and change it to dj dw plus equals error at x of I. And this is a vectorization optimization that NumPy allows us to make. And it's basically saying the same thing as what we did in this for loop, but it'll be a lot faster in execution. And let's see if this gradient step actually helps our cost function now. Alright, and it looks like in that one step we had a decent drop in the cost. So let's go ahead and write out the gradient descent algorithm now. Alright, so this function works very similar to the one we had with basic linear regression. We're storing a history dictionary, and then for each iteration we're applying the gradient descent step and then recording every 100 intervals the cost to history, and then returning history, the updated weight, and the updated bias. So let's go ahead and try out that function. Alright, so that function actually gave us a data type error, and this is because we have weight and bias as integer values, where alpha times dj dw is giving us a float 64 data type. So we can just say w is equal to w minus and b is equal to b minus, and Python will automatically handle that data type inconsistency. And it looks like our gradient descent algorithm worked pretty good here. Let's go ahead and plot the history. Alright, so here's our cost after each 100 iteration step, and let's go ahead and plot what our new predictions look like. And let's again plot what our old predictions looked like. So it turns out our new model is a little better at generalizing the data, while our previous model was good at some predictions but way off on other predictions. But now that we have our multiple linear regression model all finished, we can finally go back and use the low diabetes dataset from scikit-learn and test on a larger dataset. So let's load it. Alright, so it looks like we're looking at 442 training examples and 10 features. So before we train, let's try to understand what the data looks like a little bit. So in one training example, we have, it looks like scaled down floating point values, which is not categorical data, which is good for our case. And Y ranges from 25 to 346 with a standard deviation of 77, so it looks like we're given some good regression data to work with. Now let's go ahead and build a model. And let's run that. So as you can see, our cost function is going down after every 100 iterations. Let's plot that history graph. Alright, nice. So starting off, our cost was pretty high, and then over time it went down and kind of flatlined around the 2,800 mark. And finally, let's go ahead and make a few predictions just to see what kind of accuracy we're working with. Alright, so these are the first 10 predicted values, and let's compare those against the true first 10 values. So we can see a little comparison, and it might be easier to plot those, so I'll go ahead and do that now. Alright, so as you can see, the predicted values are generally lying around where the true values are, except there's not much variation in these predictions. There's a few reasons this could be. One is that the multiple linear regression model on its own is not very complex, so it can't really pick up complex patterns within our data. But if we increase our alpha, maybe we can get a little bit better of results. And if we plot the history. Alright, so that gave us a little bit better of results, but again, multiple linear regression alone is not very complex, so we might need to add some feature engineering or maybe use a more complex model, but it looks like with a higher alpha, we had a little bit better results. And that's about it for multiple linear regression. Anyway, thanks for watching, and let me know if you have any questions about the content.